So infrared spectroscopy is one of the main techniques that we use to identify what our product looks like, so we can verify that we made what we thought we were going to make in the lab. Functional groups are the main piece of information that infrared gives us. Looking at the infrared spectra of a compound, we can determine the kind of functional groups that are in a molecule. For example, alkane IR spectra look very, very different from, say, a carboxylic acid spectra. So in the alkane, we have carbon, hydrogen, single bonds, and that's it. But in carboxylic acid, we have a C double bond O here, and then an extra oxygen over here with an OH. And so those are going to look very different. So if we look into what the electromagnetic spectrum is all about, we need to start talking about what is infrared. So infrared is an electromagnetic radiation that happens just a little bit lower energy than visible light. And if you think about the electromagnetic spectra, cosmic rays and gamma rays and X-rays are very, very high energy, and they have a very high frequency, and they in turn have very short wavelengths. Whereas when we get down to the lower energy end of the spectrum, radio waves, microwaves, and infrared end up having very low energy and low frequency, but they actually have pretty long wavelengths. What infrared looks at in terms of organic chemistry is stretching and bending of bonds. So as the bonds stretch and bend, we can identify those stretches and bends when we put infrared radiation through our sample. So we put infrared radiation through our sample, and what happens is our molecule will absorb certain wavelengths and not absorb other wavelengths. So in infrared, when we talk about a bond stretching or bending, this is what we're talking about. So we have a bond, we can think about that as a spring, and so we're going to have some stretching and bending and vibrating. And so the next slide actually shows a really nice display of how this might work. Asymmetrical stretching and symmetrical stretching, rocking, scissoring, twisting, and wagging. So these are all ways that our molecules can be moving. Just naturally, as they exist, they have these movements, and infrared picks up on some of these energy modes that are happening within our molecule in terms of absorbing. So in general, we have an infrared spectrum that looks like this. So on our y-axis, we have transmittance. This is the IR light that goes through. So in the detector, this is what's been transmitted. And on the x-axis, we have wave number, which is reciprocal centimeters. And so it's the inverse of the wavelength. And we have our low values down here. So we have very low wave numbers here, and we have very high wave numbers here. And so it goes from 0 to 4,000 from right to left. And when we look at what's observed in these areas of the spectrum, we see that N single bond H, O single bond H, and C single bond H all occur in this area above, say, 2600. The carbon-nitrogen triple bond and the carbon-carbon triple bond, the signal is going to appear in this area in between 2000 and 2600 reciprocal centimeters. And our C double bond O, C double bond N, and C double bond C occurs even further down in this region in between about 1500 and 2000. You can imagine that it takes more energy to stretch the triple bond than it does to stretch a double bond. So you can imagine that being increasing in energy here. And so why are the single bonds way up here? And that's because that hydrogen is so light that we actually have very fast vibrations of the of the hydrogen-nitrogen bond stretching and the oxygen-hydrogen bond stretching and the CH bond stretching. And down here is the fingerprint region, and the fingerprint region is very specific and detailed, and unless you're an IR expert, like you've gone and gotten your PhD in IR, we don't really worry too much about this in this class. We primarily look at the double bonds, the triple bonds, and then these H bonds up here. Here's an example. Here's the infrared spectrum of octane. So octane is oct, which is 8. Ane means there's all single bonds. And these peaks right here are the CH bonds. It turns out that right at the 3,000 mark, right here, there's a cutoff. Anything right below the 3,000 is a carbon bonded to a hydrogen that is an alkane, so it has no double bonds on it whatsoever. And so if we look at our next spectrum, we see a peak that's above 3,000. So we're looking at this 3,000. This spectrum is for 1 octene, so it has this double bond. And so what happens is we see an additional signal up right above 3,000, and that is from the CH stretches on the double bond. So right above 3,000 means that we have an sp2 hybridized carbon CH stretch. Right below 3,000 is going to be an sp3 hybridized CH stretch, which means that it's all single bonds. sp2 means there's a double bond. And so that's really one of the main things we're going to look at with IR. This is called saturated, and this is called unsaturated. And so this is all single bonds, and then up here we have a double bond, at least one double bond. And if we go to the alkyne, which is a triple bond, and we have it at the end of our molecule so that there is an H on it, we see this very strong and very unique stretch up around 3,300. And so that's indicative of a triple bond, alkyne. But remember, it has to be on the end, because if it was in the middle, then we would have no H attached. Because remember, when you have an sp hybridized carbon, there's only the chance of having one additional atom attached. And again, the whole rest of this molecule is all sp3 hybridized, so we're going to see this nice peak below 3,000. If we were looking at the IR spectrum of toluene, so toluene is benzene, the 6-membered ring with double single bonds around and a CH3 group off of it. So if we look at that, we see a very different spectrum. Of course, here's the 3,000 mark. So much of our signal is happening above 3,000 because of all of the sp2 hybridized carbons here with H's on them. So we have a CH stretch. And then we do see some signals that are below 3,000, and that's because of the 3 H's we have here on this carbon, which is sp3. And then up here we see the combination bands from the double single, and we also see this aromatic stretch right here at 1,500. Benzene is one of the examples of a great aromatic molecule. If we're looking at carbonyls, we see aldehyde, ketone, ester, amide, carboxylic acid, and they have their own range of where they're going to appear on the IR. So this 1,700 range in the IR spectrum is going to be attributed to the carbonyl, the C double bond O, and that's going to give a different value depending on the type of carbonyl that we have. So if we look at the spectrum of carboxylic acids, we see that there's this very kind of gross, broad peak up here around 3,000, and that's from the OH. And then we also see this very strong peak here at about 1,700, which is our carbonyl. So that's the C double bond O. And so this is a typical example of what a spectra looks like for a carboxylic acid. And if we're looking at amines, the NH stretch of an amine, so if we're looking at the spectrum here of 4-methylaniline here, so on the 4th carbon is a methyl group and aniline is a benzene with an NH2. This is all stuff that you'll learn as you move forward in the class. But primarily what I want you to see here is this NH2. So this NH stretching gives us these two very unique and nice peaks up around 3,300. And because there's two hydrogens, we see two peaks. We also see the combination peaks here, and we see the aromatic peak here. And so that shows us the benzene part. When you have an amine that is primary, which means that there's only one carbon connected to the nitrogen and two hydrogens, we have two hydrogens. So we're going to see two peaks within that range. Whereas if we have an amine that's secondary, which means it has two carbons on it and only one hydrogen, that's going to just be one peak that we observe up in that 33 to 3,500 range. So the infrared spectra does give us a lot of information about the molecule. Specifically, it tells us about the functional groups present. You'll often be given a table like this one here that gives us some identifications for what functional group is going to give a signal at what frequency or wave number. And so you see there that the OH stretch is around 3,600, and that tells us about alcohols and phenols. Okay, great. So now you know a little bit about how to interpret an infrared spectra, and we'll be using this in all of our labs, so this is going to be an important technique to know and understand. Combine this video with the one that shows you actually physically how to run the instrument, and you should be all set.